Good day students, welcome to the Electrical Protection 4 practical exercise on transformer differential protection using the SEL487E relay model. The aim of this exercise is to implement transformer differential protection on one of the transformers given in the 5-bus power system network shown in the Digsilent simulation environment that is shown on your screen. The first step in conducting this exercise is to construct the network as shown in the Digsilent simulation environment on your screen. The input data to the network is shown on page 34 in your lab manual. Before you can pause this video and start constructing the network, there is something I would like to show you. The way we model transformer differential protection in Digsilent is a little bit different. This is because Digsilent does not give you the capability to induce faults on the transformer winding directly. So there is a special way of doing that. If you can look in this network, you will see that the way this transformer has been connected to the rest of the network is not the same as this transformer is connected to the rest of the network. The way this transformer is connected does not allow you to directly induce a fault on the transformer windings. This somehow allows you to simulate an internal fault on the transformer. Well, what is the difference between these two methods of connecting the transformer? In this method, we put a dummy node in between the transformer and the bus bar. This method does not. By inducing a fault on the dummy node, we can simulate an internal fault on the transformer simply because the dummy node represents the transformer bushing. This method does not allow you to induce a fault on the transformer. If you try to induce a fault on the transformer, you can see you do not have any option to calculate or to compute any type of fault. However, if you put a fault on the bus, this is not a fault that is directly on the transformer winding. So your differential protection, if it is set up in between these two bus bars, will not operate for a fault that is on this bus and on this bus, because those two faults are outside of the protected zone. The differential protection will look at the current that is flowing in that line and the current leaving that line going that side. It will not see a fault that is on this bus or on that bus. So by coming to this arrangement, we can see that by putting a dummy node in between, we can induce a fault on that dummy node. And that fault represents a fault that is on the transformer windings. So that is one way of modeling transformer differential protection. Because your current transformer sits right there and another one sits right there, it measures the current that flows there, meaning the current that rushes to this dummy node when a fault occurs here, or the current that rushes to this dummy node when a fault occurs. So by doing that, you can model transformer differential protection. So I'm going to show you how to connect a dummy node in between this transformer and the bus bar. If you already have the transformer connected up, you might want to right click it and you go to disconnect element. If your transformer was not connected up before, you would simply just click on the transformer from the component library and drag it in and drop it in there. So you go to your component library again, and under the library you choose junction or internal node. So you drop one node right there, and you drop one node on the other end of the transformer. So you right click on the transformer and you go to connect element. You connect it to that node, and you connect it to that node. Now your transformer has been connected between the two dummy nodes. However, you still need to connect the dummy node to the bus bar. So how do you do that? You go to your component library and then you choose a circuit breaker, because in between your dummy node and your bus bar should be a circuit breaker. Similarly, if you would connect a transformer out there in the field, you would put a circuit breaker before the transformer and the bus bar. For the same reason we do it in Digsilent. So you click on the bus bar, on the circuit breaker, and you connect it onto the bus bar by clicking on the bus and selecting a cubicle to connect it to. And then you connect it to your node by clicking on the node. We do the same on the other end of the transformer. And well, our transformer has been connected up. However, if you look at it, part of this network is black and part of this network looks somehow gray. This is because the circuit breakers at these junctions are open, and if you would try to get power to flow to this other end, it will not get there because these two circuit breakers are open. So to close them, you double click on it. And you can see now the rest of the network has been connected up. Right, so the relay model that we are going to be using is the SEL487E relay model. And if you haven't got it in your relay library, so this is the time to deactivate the project and import the relay. To check if you have it in your library, you open your data manager by clicking on that icon, and then you navigate to your relay library. You go to the vendor name and you check if it's listed under the list of relays that are in there. And as you can see, I have got it in my library, so I do not need to import the relay again. However, if you do not have it, please deactivate your project now, import the relay and activate your project again. From the principles of transformer differential protection or unit protection to say, you have the relay that is connected across the transformer and it's fed by two current transformers sitting on either side of the transformer. The same principle applies in Digsilent. You need to have a current transformer measuring at this end of the transformer, and you need to have a current transformer measuring at this end of the transformer. Those two current transformers must feed their currents into the differential relay. So it doesn't matter where you set up the differential relay. You can have the differential relay sitting in this cubicle. However, it still has current transformers that are connected here and at this other end. Or whether you set up the differential relay in this cubicle and still have current transformers connected at this cubicle and at that cubicle. Bottom line is you need two current transformers. So how do you do that? The first step is to set up a current transformer at this bus bar. Why? Because I have chosen to set up my differential relay at this cubicle. Similarly, if I had chosen to set up my differential relay at this cubicle, I would need to define a CT before I can do anything else at this cubicle. This CT will be measuring current at that cubicle. Although it sits in here, it is set up to measure current at that cubicle and then feed its currents back into the relay here. So to do that, you right click on the cubicle and then you go to new devices We go to current transformer. So this current transformer, I will name it CT, or let me rather name it 11 kV CT. Why? Because it's going to be measuring current on the 11 kV side of the transformer, and I'm gonna say it's at substation 3. You go ahead and you define a project type. You go to new project, but still name it 11 kV CT at substation 3, and the ratio is 100 to 1. This ratio has been specified in your lab manual on page 34. So to select a location for this CT, because by default this CT will be measuring current in its parent cubicle. Its parent cubicle is here at substation 2. That's why you see under location this CT is measuring current at substation 2. So to change its location, you go to the drop down arrow under cubicle, and then you go to select, and then you navigate to the substation or bus bar where you want this current to measure. This current transformer to measure current. So because I wanted to measure at substation 3, which is bus bar 3, I go on the drop down arrow, and then I look for the cubicle in which I want to place it. Okay, I want to place this current transformer in cubicle 4. Why? Because that breaker switch, you remember the breaker switch I spoke about earlier when we were inserting the dummy node. That breaker switch is connected to cubicle 4, and we might want to put the current transformer to measure the current that is flowing in that breaker switch. Why? Because if you connect it, say, on cubicle 3, it's going to be measuring the current that is flowing to load 1. Remember, there is a load connected on that bus bar. So be very careful when you select which cubicle to connect your current transformer. Otherwise, it's going to be measuring the wrong current. Alright. So now we can go ahead and set up our relay. So you still follow the same procedure as we have described in the earlier videos. You right click on the cubicle, you go to new device, you go to relay model. Under relay type, you go to select project type, you navigate to the relay, then the name, and well, the current transformer that we have defined has an output of 1 amp. So there is no way you are going to select a relay that has an input of 5 amps. Ideally, you would select a relay that has an input of 1 amp and matches the current transformer. You will notice that immediately when you select the relay type, the CT that we have defined in that cubicle automatically shows here, and it is already assigned to the S winding. Why? Because this current transformer already exists in this cubicle. So Digsilent looks for a current transformer in that cubicle where you are trying to set up a relay. If a current transformer already exists, it is automatically assigned to one of the windings of the relay, if not one, then all of the windings. However, because we said we will need 2 current transformers, we will need 2 windings of the relay. These that you see labeled SCT, SCT3IO, TCT, TCT3IO, those are different measuring windings of the relay. So you have an S winding that measures your phase current, and you have an S winding which is denoted SCT3IO that measures your ground current. You have another winding that is TCT which measures your phase current for your T winding, and you have the TCT3IO that measures your ground current for the T winding. And you have all other windings which is U, W, X, V, Z, etc. However, we only need 2 windings for this application because you only have 2 current transformers. However, say if you had a 3 winding transformer, you would 3 winding power transformer. Remember, the one we are dealing with now is a 2 winding transformer. If you look in the library here where my cursor is circling, we have a 3 winding transformer here. If we were protecting a 3 winding transformer, we would need more than 2 windings of the relay. However, because we only have a 2 winding transformer, we only need 2 windings for the relay. So because we need 2 windings, we will need 2 current transformers like we said. So we can go ahead and create a current transformer for our T winding. It is very important that you position these current transformers at the right places. We can see that this is measuring at substation 3. So the T winding should be set up to measure at substation 2. So we go on the create CT icon. In this CT, I'm going to name it CT 33 kV CT, right? Because it's on the 33 kV side of the transformer at substation 2. We need to run a type, and I'm still going to name it the same thing at substation 2, and that is 100 to 1 CT. Alright. By default, the location will be set to substation 3. Why? Because you already have a current transformer in this cubicle that is set up to measure at substation 3. So the same setting is adapted for this CT. It is very important that you change the location back to substation 2. So to do that, you go on the drop down arrow under cubicle, go to select, and then you want to go to substation 2, and then you look for the right cubicle to place this current transformer in. You can't place it in cubicle 1. Why? Because it's going to be measuring the current that is flowing in line 1. Remember, line 1 is this one. So this current transformer will sit here if you put it on cubicle 1, and it's going to be reading the current flowing in that line. Similarly, we can't put it in cubicle 2. Why? Because this current transformer will read this current that is flowing in this line. Cubicle 3 has nothing connected, and cubicle 4 is the one with this breaker switch that is feeding our transformer, and it is this current that we want to read. So we put this current transformer in this cubicle. Alright. So after your CT has been set up, it is very important that you confirm that your CT is in the right place. If you go to your S winding CT, make sure that it is measuring at the location that you have defined it to, substation 3, and you can see your T winding CT is measuring at substation 2. Before you continue doing anything, it is very important that you make sure that these 2 windings are connected at the right places. Otherwise, your relay is not going to operate the way you want it to, and it will always be tripping even for faults that are outside of the protected zone. So we can go ahead and set up the relay. Like I explained in my earlier videos, elements that we do not need to be taken out of service because they will cause false operation of the relay. For this application, we only need two windings, which is our S and our T winding. The rest of the windings we can take out of service because we do not need them. Alright, so comes here, we have differential and we have negative sequence. Differential is your phase differential, that's your normal differential. Negative sequence differential is based on sequence currents, negative sequence currents. It's also a differential element, however it uses negative sequence currents instead of using the positive sequence currents. So for this application, we are not using negative sequence currents, but rather normal positive sequence phase currents. So we'll take the negative sequence element out of service. Out of service. No, we do not put overcurrent protection, so we are not doing voltage protection either. We are not doing frequency, so all these elements need to be out of service. We are not doing overflux protection. Alright, so since we have taken all the elements that we do not need out of service, we can start configuring some of the settings. Very important before you do anything and before you forget, you need to configure your CT measuring adapters the right way. I strongly advise you that before you can start configuring and setting up the adapter, just go back to your winding one more time, then you check exactly where each winding is. Your S winding is on substation 3, and substation 3 is at 11 kV voltage level. Your T winding is at substation 2 and it's at 33 kV. I'll explain in a minute why this is so. So if you go ahead to configure your S winding, under your measuring adapter, you need to define the nominal line-to-line voltage because the relay makes necessary compensations. So it needs to know the voltage level and the current transformer connection so it can work out the currents. Otherwise, if your CT measuring adapters are not set the right way, you will always have differential currents even under normal operating conditions or when you do not have any fault. So it is very, very important that you give the right parameters for your measuring adapters. Because our S winding is set up for the 11 kV side, we're going to put 11 kV there. The transformer, current transformer connection, they are connected in a Y configuration. Click on OK. You go to your T winding. You repeat the same procedure. However, your T winding is on the 33 kV side, so you must give the right voltage. The connection is Y and the vector group is 0. Alright. So you can go ahead and set up our differential element. Sometimes it is specified to give certain settings as per the specifications of your lab manual or whatever assignment you may be doing. However, the default one seems pretty just fine and just does the job. So you have two slopes. You have the first slope, which can either be 35 degrees, and you have the second slope, which can either be 75 or however way you configure it. These two slopes are restrained. There is an unrestrained differential element that is set to a value that is very, very high. The reason for the unrestrained differential element is to provide fast tripping for internal faults that are so severe that you do not want a time delay. So the unrestrained differential element responds very, very quick to ensure that you have minimal damage to your transformer. The first slope and the second slope are restrained and they might not operate very, very fast, and that's why the relay provides you with an unrestrained differential element to give you fast fast tripping with no time delay. Alright. So when you're done setting up your relay, click on OK to adapt the settings for this relay. Before we can do anything else, like I explained in the earlier videos, it is very, very important to run your load flow just to make sure that you haven't made any mistakes and the system is still able to compute the load flow successfully. Alright, so let's go ahead and run our load flow. Execute. Oops, that doesn't look too good. Let's see what the error is. Okay, there's something that I forgot to tell you. These dummy nodes that you insert in the network, you need to define their voltage level. If you don't define the voltage level, you will keep on getting this error. The voltage level of this dummy node should be matched with that bus bar and the high voltage on this side of the transformer. The voltage level of this dummy node should be matched with that of this bus bar and that of the transformer on this side. So let's go ahead and alter the voltage level. Oops, that was too high. 110 kV. You need to change it to 33 kV. And for this one, we need to change it to 11 kV. Okay, so we can go ahead and try to run our load flow one more time. We need to make sure that the load flow runs before we can do anything else. So you go and compute the load flow. Oh, and there it goes. Our load flow runs. So now we can start inducing faults and see how the relay behaves. So we need to pull up the differential plot. So to do that, we right click on the cubicle, we go to show, we go to differential protection plot. So we get a differential plot there. Now we need to start inducing faults. Then we see if the relay trips and if it operates the way we want it to. So we can start inducing faults on the network. We can start on that bus bar. We right click, we calculate short circuit. So it's a 3-phase short circuit. Execute. We go back to our differential plot. You can see the relay does not operate because you see your tripping time is given as 999, meaning it's never going to operate. It will keep on waiting for a while because it does not see that fault, simply because it's outside of the protected zone. Remember, I explained earlier that a fault that is on this bus bar is regarded as outside of the protected zone. Why? Because your current transformer sits right here and the other one sits right here. Anything that is on the other side of the current transformer is regarded as outside of the protected zone. And anything that falls in between the two current transformers is within the protected zone. So, coming to this dummy node that we have placed here, by inducing a fault on that dummy node, the system thinks that it is the same as inducing a fault on the primary winding of the transformer, simply because this is exactly the same point as that one. So if you right click and induce a short circuit on this dummy node, well, this fault is within the protected zone because it falls in between the two current transformers. So we are expecting the relay to trip. And there we go. The relay operates in 0.015 seconds. You can move on to the next dummy node and induce a fault on the secondary side of the current of the power transformer. And again the relay operates. Why? Because the fault is within the protected zone, and that implies that the fault is inside the transformer. Remember, when you do differential protection on the transformer, you want to protect it against faults that are within the transformer, not faults that are outside of the transformer. That's why for anything that falls in between the current transformers, the relay will operate. If we go ahead and induce the fault on this bus bar, we do not expect the relay to operate. Why? Because it's outside of the protected zone. And there we go, the relay does not operate. You can put the fault anywhere else in the network, even on that line. For as long as it's outside of the protected zone, this relay will not operate. Since the fault that we have conducted was a 3-phase symmetrical, we can conduct one more fault, say face-to-face fault. So we try a face-to-face fault on that bus bar. Go to calculate short circuit, and we choose a 2-phase fault. Well, the relay does not operate again. Why? Because it's outside of the protected zone. If we conduct a face-to-face fault again on this dummy node that is inside the transformer, the relay operates in 0.015 seconds. If we conduct this same fault on this bus bar, we see that the relay does not operate. Why? Again, for the same reason, the fault is outside of the protected zone. You can conduct this fault anywhere in the network, even on this bus bar. We do not expect this relay to operate. And there we go, it does not operate. Right, we can conduct a phase to ground fault again, just to validate that the settings also work for ground faults. So we can go ahead and conduct a phase to ground fault on that bus bar. Single phase to ground, execute. Still, it's outside of the protected zone and the relay does not operate. We conduct a single phase to ground fault inside the protected zone, which is supposed to be inside of the transformer. Well, the relay operates, which is what we expect it to do. The relay still operates. If we conduct a single phase to ground fault on this bus bar, we do not expect the relay to operate. Why? Because it's outside of the protected zone. And you can see the relay does not operate. So you can go ahead and try to set up differential protection for that transformer, and also conduct different faults at different locations of the network, and then you see how the relay behaves. And ladies and gentlemen, that concludes today's exercise on transformer differential protection. Thank you very much.